So this is a review of the test. Let me just, so I'm just going to go over these one at a time. So the motion of a car is represented on a position versus time graph by a straight line that slopes up to the right. This means the car has. So let's pull this up. Oh, this is from the last slides, the thing that I was talking about. So let's just pull up. And so here's my, in a position versus time graph, it slopes up and to the right. It's a straight line that slopes up and to the right. If you remember, we said that the slope in a position versus time graph, if you remember how you take the slope, it's the change in position, right? If this is T2 and this is T1 and this is X1 and this is X2, then this is X2 minus X1 and this is T2 minus T1. This here, right? The slope is the rise over the run, and so the slope is X2 minus X1 over T2 minus T1. It's that over that. That's how you take the slope in a graph. But that's just the thing we call the average velocity. Right? And so the question says, let me just go back to it. The motion of a car is represented on a position versus time graph by a straight line that slopes up and to the right. This means that the car has a constant positive velocity, right? So when the slope is up, it's positive. Let me just get back to here. Right? A slope this way is positive. It means this number is positive and this number is positive. So it's constant because it's a straight line. The slope anywhere along that line is the same if it's a straight line. And so if the velocity was increasing, which is the third choice, it would have to look like that, where the slope is constantly changing. Or if the velocity is decreasing, it would have to look like that. So that's the first question. So the next question is, which of these is not a physical quantity? If you remember, a physical quantity is a measurable property of matter. And so time is a physical quantity. Force is a physical quantity, mass is a physical quantity, but grams is a unit. Grams is a unit of mass. It's not a physical quantity, so the answer is grams. Which of these is not a vector? So acceleration has a magnitude. You accelerate in a direction. A force is applied in a direction. Displacement has a direction. That's just a change in two positions. And so from one place to another place, that's a direction. But mass does not have a direction. So it could be moving in a direction, but that's its velocity, or that's its acceleration. Okay, next question. Where am I here? There we go. Let me scroll down a little bit. A force of 150 newtons acts to the right on an object, while a force of 100 newtons acts to the left. The magnitude of the net force is, and so let me go back to my drawing here, and I can say there's a force of 150 newtons going that way and a force of 100 newtons going that way. And so the net force is the difference between those two. It's 150 newtons minus 100 newtons, which is 50 newtons. Right? Because those two are working against each other. They're kind of canceling each other out a little bit. So the next question, let's get back to here, is which choice below is a fundamental physical quantity? Right, and so here you kind of have to remember that there were only 7 fundamental physical quantities, and mass was one of them. If you remember, let me just write a few of these down. So velocity is change in position over change in time. So it's a derived physical quantity. It comes from other physical quantities. Acceleration is change in velocity over change in time. So it's also not a fundamental quantity. Force is mass times acceleration, also not a fundamental quantity, physical quantity. But mass is a fundamental physical quantity. And so mass is the answer to that. Question 6. At time t1 equals 2 seconds, a toy train is in position x1 equals 2 meters. And so I'm going to come over here. I'm just going to write these down. T1 equals, I guess I'll switch back to it just so you can read it with me here, if you don't have it with you. So this is question 6. At time T1 equals 2 seconds, position x1 is equal to 2 meters. At time T2 equals 4 seconds, x2 equals minus 8 meters. It says, what's its average velocity over this time? Right, so let me just come back to here. Right. If you remember, the definition for average velocity is change in position over the change in time. That's x2 minus x1 over t2 minus t1. That's minus 8 meters minus 2 meters. Right? I'm just plugging in over 4 seconds minus 2 seconds, which is minus 10 meters over 2 seconds, which is 5 meters per second. Sorry, minus 5 meters per second. There we go. So, correct answer is minus 5 meters per second. Right. So a car starts from rest, this is number 7, and speeds up to 4 meters per second in 5 seconds. What's its acceleration in meters per second squared? Right? And so this is another one where I'm saying a car starts from rest, and so that means v1 equals 0, and speeds up to 40 meters per second. v2 is 40 meters per second. And then I can pick t1 equal to 0 because all it's saying is here is the time is 5 seconds, and so I'll say t2 equals 5 seconds. And so the acceleration is the change in velocity over the change in time. It's 40 meters per second minus 0 meters per second over 5 seconds. I can either say that the time allowed was 5 seconds, or I can say t2 is 5 seconds and t1 is 0. 5 minus 0 is 5. And so this is 8 meters per second, or 8 meters per second squared. So that was that one. I'll go back to the questions. In a position versus time graph, a horizontal line means the object is so. So let's do this. So once again, if I have a position versus time graph, that's what a horizontal line looks like, right? And what that means is its position is never changing. Wherever I go on the graph, if I want to find its position, I have to go horizontally across to the y-axis. In this case, it's the x-axis, but it's the vertical axis, right? Anywhere on here, I just go to the left and find the position on this axis, and you can see that it's not changing. And so a horizontal line in a position versus time graph means the object is at rest, right? In a velocity versus time graph, that's the next question. So the next question says, in a velocity versus time graph, a horizontal line means the object so I can find my way back here, right? It's the same thing, right? If a horizontal line of velocity versus time graph means the velocity is constant, right? Because wherever I am on the line, if I want to go find out what the velocity is, I have to go over to the axis, and it's a constant velocity. So the next one says, in a position versus time graph, the slope is the velocity. We've already talked about that, right? It's the change in position. The slope is the change in the vertical axis over the change in the horizontal axis. In a position versus time graph, it means the slope is the change in position over the change in time, and that's the velocity. So, for the dropped ball, this is probably maybe one of the harder problems on the test, right? For a dropped ball, we said it falls to the ground in 3 seconds. There are a few ways to do this problem. One is just the distance for an object that's dropped 1/2 from rest is 1/2 at squared. And so that's 1/2 times 10 meters per second squared, because that's the acceleration of gravity, times 3 seconds squared. 3 squared is 9, times 10 is 90, divided by 2 is 45 meters. Right? You could also say, well, if it falls under the acceleration of gravity, its final velocity is just the acceleration times the time, if it fell from rest. And so that means 10 meters per second squared times 3 seconds, which is 30 meters per second. When it hits the water, you would really call that the V2, right? Times the total time, if I wanted to say it that way. Right. It's the speed is how long it accelerated times how long it was accelerating at that rate, assuming it started from rest, which it does if it's dropped. And so that means its final velocity when it hit the water is 30 meters per second. Its initial velocity is 0 because it was dropped from rest, right? And so its average velocity is 15 meters per second. Initial plus final divided by 2, right? And so the distance it travels is just the average velocity times the time, which is 15 meters per second. Dang it, I had it on the wrong screen. Let me start it here. So these are the ways to solve it. I'll start over. This is I'd say the most straightforward way is to recognize that for an object that's falling from rest, the distance it travels is 1/2 at squared, which is 1/2 times 10 meters per second squared, which is the acceleration of gravity. That's how fast it's accelerating, times the time it was in the air, 3 seconds squared. If you multiply all that out, 3 squared is 9, times 10 is 90, divided by 2 is 45. That's the easiest way to do it. You can also say that its final velocity is just the acceleration times the time. That comes from the definition that the change in velocity is equal, the acceleration, I'll write it over here, is equal to the change in velocity over the change in time. If V1 is 0, this is just V2 over the change in time, or with a little algebra, you can say V2 is equal to the acceleration times the change in time, which is what I wrote here. That gives you the final velocity. It doesn't give you the answer. But if the final velocity is 30 and the initial velocity is 0, that means the average velocity is 15. It did 15 meters per second for 3 seconds, which is 45 meters per second. Either one of these ways would solve that problem. The next question asks, what's its speed, which we just answered. Let me go back to that. What's the speed of the ball 3 seconds after it's dropped from the bridge? So it was 30. So a ball of mass 0.2 kilograms is struck by a bat with a force of 40 newtons. What is the magnitude of the force that the ball exerts on the bat? Well, it's the same as the bat exerts on the ball by Newton's third law. So if the bat hits the ball with a force of 40 newtons, the ball hits the bat with a force of 40 newtons. So those are just 40 newtons. Newton's third law is very simple, but it's often conceptually very challenging because it doesn't match what we think would happen. It turns out that the force due to the ball on the bat is exactly the same as the force due to the bat on the ball, just in the opposite direction. So question 14 says a baseball of mass 0.2 kilograms is struck by a baseball bat with a force of 40 newtons. What's the acceleration of the ball? Well, we use Newton's second law for that. Let me erase this. We can say force equals mass times acceleration. That's Newton's second law, or acceleration equals force divided by mass. That's 40 newtons divided by 0.2 kilograms, which is 200 meters per second squared. So in this next problem, a weight is hanging vertically from a cable that's attached to the ceiling. What is the tension in newtons in the cable? And so the only subtlety there is you have to multiply by gravity. And so let me switch over to here. Right, if I have a cable and I have a weight hanging from the cable, the mass is 5 kilograms, right? I know that the force of gravity pulling this thing downward is mg, which is 5 kilograms times 10 meters per second squared, which is 50 newtons. 50 newtons, right? But if the object is not moving, right, it's just hanging there, then there must be an equal and opposite force, not in Newton's third law version, but something has to be pulling up to cancel this out, otherwise the ball's going to fall. And so the only other thing that's acting is the tension, and so the tension has to be 50 newtons upward, which is one of the choices there. The Fi prefix meaning a million is mega. Which of these is a derived physical quantity? We talked about that earlier. Force, velocity, acceleration. All these guys, these three here, are fundamental physical quantities. They're not made up of other physical quantities. Right? Number 18, the dimensions of acceleration are. So, back to here. So acceleration is by definition the change in velocity over the change in time. Velocity is a length over time divided by time, which is length over time squared. And so on your test, that would be choice D. A cup is sitting motionless on a horizontal table. The friction force acting in the cup is 0. If there was a net force acting on the cup in the horizontal direction, the cup would move. It's only when you start pushing the cup that friction starts acting. So what is the Newton's third law equal and opposite force for the normal force pushing up on a cup that is sitting on a horizontal tabletop? So if I set my cup on the horizontal tabletop, wait, where am I at 4 here, right? Maybe I can do this. There's my cup, right? It's sitting on a horizontal tabletop, like that, say, right? It's got some ice in it. Right? So what is the equal and opposite force for the normal force pushing up on the cup? So the cup has force of gravity pushing down, and then it's got a normal force pushing up. Those have to be equal and opposite because the cup's not moving, right? It's just sitting here. And so these two have to be the same size. We're asking what's the equal and opposite force for this guy, the Newton's third law, equal and opposite force, right? Those forces are the form, I do this to you, you do it back to me. So we talked with the baseball bat, right? The ball hits the bat, it puts a force on the ball puts a force on the bat, equal and opposite, right? And so this normal force is the table pushing up on the cup, and so the equal and opposite force for that is the cup pushing down on the tabletop. That's answer B. The cup pushing down on the tabletop. What is the gravitational force acting between two people with mass 100 kilograms standing 1 meter apart? Right. The answer to that is B. It just comes from the formula. I did this exact example in the lecture. It's the force of gravity. It's this constant G times mass of 1 times mass of 2 over the distance between them squared. If you want, you can call that an R. It doesn't matter. It just represents it. And so this is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times 100 kilograms times 100 kilograms over 1 meter squared. This is just a 1. This is 10,000. This is 10 to the minus 11. This is 6.67 times 10 to the minus 7 newtons, or less than a millionth of a newton. not very big. And so it's choice B on here. Consider two planets A and B that have the same mass. Oh no, NASA launches a spacecraft. What happens to the force of gravity as it gets higher? The force of gravity decreases for the reasons I just said a minute ago. As D gets bigger, this value has to get smaller. As the denominator gets larger, as I get farther and farther apart, the gravitational force between two objects gets smaller and smaller. Let me try this one. Consider two planets A and B that have the same mass. If B has a larger radius, then the gravitational pull on B will be larger than A or smaller than A, or the planets will have the same gravity on their surfaces. Well, it turns out, once again, for similar reasons, I guess. If I want to look at the force of gravity on a planet, let me just pull this equation up here again, right? Let's say the force of gravity on a planet, so it's G times the mass of the planet times the mass of me, maybe, over the distance. It's the distance between our centers. So when it's a planet, it's just the radius of the planet. It's the distance between me and the center of the planet squared, right? If you have two planets that have the same mass, my mass isn't going to change, but if two planets that have the same mass, the guy with the smaller radius is going to have the greater gravitational force on its surface, right? If their masses are the same and they're acting on the same object with the same mass, then the more compact object is going to have the stronger gravitational force. It turns out that Saturn has about 100 times the mass of the Earth, but because it's 10 times bigger in radius, those kind of balance out. And if Saturn had a surface, you would have about the same gravity on Saturn as you have on the Earth, despite the fact that they're very different planets. And so the more compact you are for a given amount of mass, the greater your gravity at your surface. So a backpack of mass 30 kilograms is carried 2 meters over a horizontal field. What's the work done on the backpack? Well, this is a little bit of a trick question, because the work done is the force times the distance moved in the direction of the force. And when you're carrying a backpack, while you're walking, you're lifting up on the backpack, not so much pulling forward on it. Once it's moving, it just keeps moving. And so the force is upward, but the distance is horizontal, and so the answer is 0. If you're just moving it horizontally, it's no work. No work is being done. And then the last question, here we go. The force of 20 Newton acts on a toy car of mass 0.4 kilograms over a distance of 0.6 meters. The car is initially at rest. What is the work done in joules on the car? Right, the work done is force times distance, and so it's just this 20 newtons times 0.6 meters, or 12 joules.